You know, in our everyday lives, when we try to make something perfect, it's almost always just a series of really messy, subjective guesses.
Oh, absolutely.
Think about it, like you tweak a recipe by adding an extra pinch of salt, or you keep rearranging the furniture in your living room.
Right, or trying a bunch of different side streets to find the fastest commute to work.
Exactly. You just kind of stop making changes when it feels, well, good enough.
Yeah.
It's totally subjective and honestly pretty imprecise.
It's entirely based on trial and error. We just guess and check until we run out of patience.
But if you step into the world of mathematics, that guesswork completely vanishes.
It really does.
The concept of perfect is no longer just a feeling or an opinion. It becomes this highly specific, calculable coordinate. Perfect becomes an absolute truth.
Yeah, it's math.
So today, we're doing a deep dive into the underlying mathematics of that perfection. We're looking at optimization theory.
Which is such a fascinating area.
It really is.
Yeah.
And we're specifically focusing on a foundational framework from Insert Chapter 6, Section 6.4. That gives us the mathematical definition of optimization.
Right. It's the shift from saying, I think this is the best setup, to saying, I can mathematically prove that nothing better exists in this universe.
Oh, I love that. To really understand how this shapes our reality, we've pulled together a really great stack of sources for you today.
We had some great stuff to cover.
We do. We're starting with those core theoretical notes on mathematical operational rules. And then from there, we'll look at 3 completely distinct real-world domains.
Just to see how this math powers modern engineering.
Exactly. Specifically, aerospace, electronics, and computing.
Yeah.
And finally, we'll ground all of this high-level theory by looking at a practical computational script, one that solves a very tangible physical optimization puzzle.
Which I think will really help visualize it.
For sure. Okay, let's unpack this. Before we can start building rockets or, training artificial intelligence, we need a universal language to define what the best actually looks like.
We do.
So how does optimization theory actually define the goal?
Well, at its core, optimization is fundamentally about finding extreme values.
Okay.
We're looking for the absolute maxima and minima of a differentiable function, let's call it f of x, within a specific defined boundary or domain, which we'll call I.
Right.
If you imagine any changing scenario as a continuous curve on a graph, the highest point on that curve is your maximum.
Makes sense.
And the lowest point is your minimum. To find those exact extreme points, mathematicians look for what are called critical points.
Critical points. Okay.
Yeah. A point in your scenario is a critical point if the first derivative of the function at that exact moment is 0.
I love visualizing this because staring at pure calculus on a page can be, well, a little abstract for me.
Oh, for most people, definitely.
So I like to think about this as a mountain hiking analogy.
Okay, let's hear it.
Imagine you're hiking up a really steep trail. As you're climbing up the mountain, the slope under your feet is positive.
Right.
In calculus terms, the first derivative of your elevation, which is really just your rate of change, is greater than 0.
Yes,
Your
exactly.
calves are burning, you're gaining altitude, the slope is positive.
That's a perfect physical representation. The rate of change is actively increasing your elevation.
Right. But then you finally reach the very peak of the mountain. Just for a brief moment, the ground right under your boots completely levels out.
Yep.
It's perfectly flat. The slope is exactly 0. That is our critical point.
Spot on.
And then you take another step forward and you start walking down the other side of the mountain. Now the slope is negative.
Because you're going down.
Exactly. The derivative is less than 0. Because you went from a positive climbing slope, hit a flat 0 point, and then went to a negative descending slope, you've just mathematically proven that you were standing at a local maximum.
You found the peak.
You found the peak.
That is the first derivative test in a nutshell.
Yeah.
And naturally, the exact reverse implies a local minimum.
Right, going into a valley.
Exactly. If you're walking down into a valley, so you have a negative slope, then the ground levels out at the bottom to 0, and then you start climbing back up a positive slope.
You know you hit the bottom.
Yeah, you've hit the lowest point, the local minimum.
Yeah.
But there's a crucial nuance here that often catches people off guard when they first study this.
Oh, really?
Yeah, it's called an inflection point.
Oh, the dreaded false summit.
Exactly. Imagine you're on that same mountain hike, you're walking up the positive slope, calves burning, and you reach a flat plateau.
And you're so relieved.
Right, you're thrilled it's flat. The slope is 0. You might logically think, I'm at the top.
I've been there.
But when you walk across the plateau and continue on, the trail just goes straight up the mountain again.
Ugh. The worst.
The slope never actually changed from positive to negative. It went from positive to 0 and then back to positive.
Ah, I see.
Because the first derivative didn't change signs, that flat spot is neither a peak nor a valley. It's just a pause, an inflection point.
Wow, okay. So the first derivative test is great for feeling out the slopes before and after the flat spot.
Yes, exactly.
But looking at the sources, there's actually a faster way to figure out if your flat spot is a true peak or a valley without having to, like, check the trail on either side, right?
Yes, there is.
The second derivative test.
Yeah, the second derivative test is the ultimate mathematical shortcut. Instead of checking the slope before and after your critical point, you take the second derivative of the function.
Okay, wait. The first derivative tells you the slope.
Right. And the second derivative tells you how the slope itself is changing. It measures the curvature.
The actual bending of the line.
Precisely. If you evaluate the second derivative at your critical point where the slope is 0 and the result is a negative number, it means the curve is bending downward, like a frown.
Okay, a frown.
That confirms your critical point is a local maximum. You're at the top of the curve. On the flip side, if the second derivative is a positive number, the curve is bending upward like a smile.
And that's a minimum.
Yes, that guarantees you're at a local minimum, the bottom of the valley.
Okay, but wait. If a negative number means it's a peak and a positive number means it's a valley, there has to be a scenario where the second derivative lands dead on 0, right?
Yes, there definitely is.
What happens then?
That's the exact limitation of the test. If your second derivative is exactly 0, the test completely fails.
Oh, wow.
It just fails. It gives you absolutely no useful information about the curvature. In that specific scenario, you have no choice but to fall back to the first derivative test and manually check the slopes on either side of the point. Or you have to start using even higher order derivatives to find out what the curve is doing.
Math really doesn't let you cut corners.
It really doesn't. And there's one more vital rule to keep in mind here.
What's that?
When you're looking for the absolute highest or lowest possible values over a closed interval, you can't just look at the critical points inside your boundaries.
By closed interval, you mean like defined borders on the map.
Yes, from point A to point B.
Right, because the highest point might not be a natural peak at all. It might just be where the map ends.
Exactly. A closed interval has strict boundaries. You must evaluate the function at all the internal flat spots, but you also have to evaluate it at the literal boundary points of your domain.
Oh, I get it.
Sometimes the absolute highest or lowest value occurs at the very edge of your defined problem. If you only look for the flat spots where the derivative is 0, you might entirely miss the true maximum that's sitting right at the boundary line.
Okay, so we've mapped out the theory. We understand derivatives, critical points, and the rules of the terrain.
Right.
Now let's see how engineers take this abstract math and apply it to the physical world. Let's look at how they manipulate these extreme values to literally make things fly.
Oh, aerospace engineering is one of the most unforgiving applications of optimization.
For sure.
The stakes couldn't be higher.
Right, because if you get the optimization wrong here, an aircraft runs out of fuel over the ocean.
Exactly.
The sources detail how aerospace engineers use this exact calculus to optimize the lift-to-drag ratio for aircraft.
Yes, the L/D ratio.
Right. Maximizing this ratio is kind of the holy grail of flight. You want to extract the maximum amount of lift for the absolute least amount of drag.
Which stretches out your glide range and drastically cuts fuel consumption.
And this isn't just a simple formula you plug numbers into, is it?
No, not at all. The equation for the glide ratio balances two competing physical forces.
Okay.
On one hand, you have parasitic drag. We call the coefficient for this CD0. This is the air resistance caused by the sheer shape and bulk of the plane pushing through the atmosphere.
Right, like sticking your hand out the window of a car.
Yes. If you've ever stuck your hand out the window of a moving car, you've felt parasitic drag. The faster you go, the exponentially worse it gets.
But then you have the other side of the equation, induced drag.
Right. Induced drag, which involves a factor K, is the penalty you pay for creating lift in the first place.
How so?
It's the turbulence and vortices created off the wingtips as the wings generate upward force. Paradoxically, induced drag is actually worse at slower speeds.
Wait, really? Slower speeds?
Yeah. So the engineers are fighting a war on two fronts. Go too fast, and parasitic drag tears through your fuel. Go too slow, and induced drag pulls you out of the sky.
Wow. So they use calculus to find the exact truce between those two forces.
Exactly.
They take the complex equation governing both types of drag and the lift coefficient.
Yeah.
and they take the derivative.
They find the critical point.
Right. They look for the exact point where the rate of change is 0, and the math simplifies down beautifully.
It does.
The optimum lift coefficient is found exactly where the penalty of parasitic drag and the penalty of induced drag cross paths and minimize each other. I think the equation is the square root of CD0 over K.
Yes, mathematically, they're finding the exact peak of the mountain just translated into aerodynamic efficiency.
What's fascinating here is that we can take this exact same mathematical logic, finding harmony between competing forces, and apply it to a completely different engineering domain.
Electronics.
Exactly, electronics.
It's a brilliant pivot. We just saw how optimization manages physical friction in the air. But what happens when the friction isn't wind, but electrical resistance in a wire?
Right. In circuit design, a foundational problem is achieving maximum power transfer.
Yes.
You want to deliver the maximum possible amount of power to a load, let's say a speaker or a motor, from a power source, like a battery.
Okay.
Now, the battery has its own internal resistance, the Thevenin resistance.
Right.
And the load has its own resistance.
And the mathematical equation for the power delivered to the load is a complex fraction involving the voltage, the internal resistance of the source, and the resistance of the load itself.
Now, when you look at that power equation, your human intuition screams that less resistance must equal more power.
Oh, absolutely.
I mean, resistance literally eats up energy and turns it into heat. So naturally, wouldn't you want 0 resistance on the load to get the absolute maximum power out of the battery?
It's such a logical assumption, but the calculus completely disproves our intuition.
Really?
Yeah. If you actually have 0 resistance on the load, like just connecting a wire directly from the positive to the negative terminal of battery, you don't get maximum useful power.
What do you get?
You just get a short circuit. The battery burns up all its energy fighting its own internal resistance, creating nothing but heat. You need some friction, some load resistance to actually harness the power.
So how do you find the perfect amount of resistance? You go back to the first derivative test.
Exactly.
You take the derivative of the power equation with respect to the load resistance, and you set it to 0. You find the critical point.
And when you solve that derivative, a stunning mathematical truth falls out. The calculus proves that the maximum power transfer occurs precisely when the load resistance perfectly matches the internal resistance of the source.
Oh, wow.
Yeah. If the internal resistance is 50 ohms, your load must be exactly 50 ohms. If you make the load resistance any lower, as intuition suggested, the power actually drops.
That's crazy.
Harmony, not elimination, is the key to maximum power.
Here's where it gets really interesting. We've optimized physical hardware. We've balanced aerodynamic friction for jets. We've matched electrical resistance in circuits.
Right.
But now we're stepping entirely into the digital realm. We're looking at computing, where optimization theory runs invisibly in the software we use every single day.
This is the big one.
We're talking about training neural networks.
Training in artificial intelligence is, at its absolute core, an optimization problem.
It's all just math.
It really is. When an AI is learning to recognize human speech or generate an image, it isn't magically getting smarter, it's systematically minimizing a loss function.
The sources describe this loss function as creating an error surface.
Yes.
It's like this massive multidimensional mathematical landscape made up of all the variables and weights inside the AI model.
Millions or billions of them.
Exactly. And every point on that landscape represents a specific configuration of the AI's brain. And the height of the landscape at that point represents how many errors the AI is making.
Right, so the overarching goal of the AI is to navigate this landscape and find the absolute deepest valley, the lowest possible point of error.
We're back on the mountain hike, but this time we're looking for the absolute bottom.
Yes, the global minimum.
The challenge is this landscape might have billions of dimensions. You can't just draw it on a graph and look at where the bottom is.
No, you definitely can't.
I love visualizing this process, which is called gradient descent, by the way, as being completely blindfolded on a rugged, hilly landscape.
Okay, that's a great image.
You can't see the bottom of the valley,
Yeah.
but you can feel the slope of the ground directly under your boots.
And feeling the ground is pure calculus.
Right.
The computer obviously doesn't have boots. Instead, it takes a tiny mathematical sample of the error rate in its current position. It calculates the first derivative, the slope. Because it's a multidimensional space, this slope is actually called the gradient.
So the AI feels which way the mathematical ground is tilting downward the steepest.
Yes.
It calculates the slope, takes a small step downward by adjusting its internal weights, and then stops.
Right. Then it evaluates again.
It recalculates the slope from its new position, feels the downward tilt again, and takes another step. It does this millions of times.
Yeah.
Step, calculate slope, step, calculate slope.
Exactly. It's iteratively feeling its way down the error surface. If we connect this to the bigger picture, this entire multi-billion-dollar artificial intelligence industry relies entirely on the first derivative test.
Wow, that really puts it into perspective.
Doesn't it? The training algorithm only stops it and only converges when it finally reaches a valley floor where the ground levels out.
And how does it mathematically know it's at the bottom?
Because the gradient, the rate of change, hits 0.
It's the exact same map as the peak of the mountain or the optimum lift of the airplane, just scaled up to billions of parameters.
That's the beauty of it.
To really ground all of these incredibly high-level rocket and AI applications, our final source is a practical computational script.
Oh, yes.
It's a piece of Python code that tackles a classic, totally tangible optimization puzzle that you could actually do at your kitchen table.
It's the perfect way to demystify the theory and see the machine actually execute the math.
The puzzle is this. Imagine you have a flat, square sheet of cardboard. Let's say the side length is S. You want to cut equal square corners out of the flat sheet so that you can fold the sides up and tape them together to make an open box.
Classic geometry problem.
Exactly. The objective is to figure out exactly what size squares to cut out of the corners to maximize the total volume of the resulting box.
Because if you cut tiny squares, the box is very wide but incredibly shallow, so it holds almost nothing.
Right.
But if you cut huge squares, the box is really tall, but the base is so narrow it also holds almost nothing.
There's a Goldilocks cut that creates the maximum volume.
This raises an important question.
What's that?
If we're using a computer script to solve this, how does it systematically tackle the problem without just guessing 1,000 different corner sizes? We established that optimization isn't about guessing.
Right. It writes an equation for the volume of the box based on the size of the cut. And then it does exactly what a mathematician would do on paper.
It takes the derivative.
Yep. It calculates the first derivative of that volume equation and finds the critical points, the flat spots, where the rate of change is 0.
But the script is smart enough not to just trust the first flat spot it finds.
Oh, because of the inflection points we talked about.
Exactly. It actually applies the second derivative test to confirm it has found a true peak.
Oh, that's cool.
Yeah, it calculates the curvature at that specific cut size. It checks to ensure the second derivative is a negative number.
A frown.
A frown, exactly. Proving the curve is bending downwards, meaning it's a peak volume, not a minimum volume. Finally, the script visualizes this perfectly optimized box for the user.
What I absolutely love about this script is that it proves a profound point for you listening at home.
It really does.
The exact same underlying calculus that works on a piece of scratch paper when you're trying to fold a cardboard box is the exact same mathematical logic that's driving a massive neural network or keeping a jet in the air.
It's a universal language.
It really is. Optimization is not just arbitrary trial and error. Whether an engineer is trying to find the ultimate glide ratio for an aerospace vehicle by balancing air friction, or an electrician is matching resistance for maximum power transfer.
Or a computer sliding down the gradient of an error surface.
Exactly. To teach an AI how to understand human speech, or if you're just folding a simple cardboard box, it all completely boils down to finding those critical points where the rate of change hits 0.
It's about finding the exact, absolute coordinate where things stop getting better and start getting worse.
So what does this all mean for you listening right now? Well, it might be worth viewing your own workflows, your own daily decisions, as surfaces to be optimized.
That's a great way to think about it.
We might not always break out a whiteboard and use calculus to organize our day, but we're constantly navigating these slopes. Where are the critical points in your daily life?
Where's the point of diminishing returns?
Right, where adding more effort or more resistance, like the electrical circuit, actually starts hurting your overall output.
It's a very powerful lens to view the world through. It turns subjective frustration into a solvable equation.
Okay.
But as we wrap up this deep dive, I want to leave you with a puzzle to mull over on your own. It builds directly on what we discussed during the computing and AI section.
Oh, I love a good puzzle. Let's hear it.
We talked about how the gradient descent algorithm is essentially a blindfolded hiker stepping down an error hill until it hits a flat bottom, a minimum where the derivative is 0.
Right.
But here's the problem. The multidimensional landscape of a complex neural network is massive and incredibly bumpy. It's not just one smooth bowl.
Okay, yeah.
So, if the AI algorithm is blindly stepping down the steepest slope it can feel, what happens if it gets stuck in a shallow local minimum crater high up on the mountain instead of reaching the true global valley at the very bottom?
Oh, man.
Without being able to take off the blindfold and see the whole map like our simple box folding script can do, how does the machine ever really know it has hit true rock bottom and hasn't just settled for a pothole?
Wow, that is a deeply fascinating question to chew on. Is the AI truly perfect? Or is it just mathematically trapped in a local crater? Thanks for taking this deep dive with us today. Keep questioning the slopes around you. We'll catch you next time.